Hi, Dr. Jahan.
Hello, good morning, everyone. I make you host, so I think you can control the meeting. But yeah, we can start
Yeah,
in 1 minute. Yeah.
I have started the recording.
Hi, Priya.
Hi, Dr. Luo.
Hi. Should I share my screen or?
No, actually, Dr. Jahan will introduce and then I will introduce and then you should carry on. So, Dr. Jahan, can you start?
I can
Yeah,
share
sure.
my. Okay, yeah.
Yeah. Thank you, Dr. Loof, for joining us. And thank you, everyone, for joining today. We have a guest presenter today. And then Priya organized this entire event. So I give her the floor to introduce Dr. Lu and then start the meeting. Thank you, everyone.
Good morning, all. Welcome to our WIDS virtual seminar. So, today we have our special guest, Dr. Luo. And a little bit about her. She's specialized in natural language processing, information retrieval, and artificial intelligence. And she's an associate professor in Management and Information Systems Department. And she has published over 110 journals and conference articles, and also a recipient of prestigious Best Paper Awards at ACM Conference on Bioinformatics, Computational Biology, and Health Informatics, and International Conference on Human-Computer Interaction. She also collaborates with multidisciplinary researchers from various institutions on funded projects supported by NIH, NSF, and industry partners. Today, she is going to talk about artificial intelligence, large language models, and their applications in health informatics and interdisciplinary research. Here is the floor to Dr. Luo. Now it's all yours. Please carry on.
Thank you. Okay, let me find my. Oh, screen one. Why I cannot? Screen one. So, can you see my slides?
Yeah, we can.
Okay. Sounds great. All right. Thank you everyone for attending my presentation today. And the topic is about AI and large language model application to health informatics and interdisciplinary research. So I'm going to talk about from health informatics to basic computer science, natural language processing, and also talk about how we can apply these techniques to the network security. And
Dr.
a little
Luo,
bit.
sorry, it's not the entire screen. I can see the bits and pieces of it. It's not on the full screen.
Oh, okay. Let me okay. Let me share my screen. Put that on the full screen.
It is showing started screen sharing, but yeah, yes, now it's full. Yes.
Okay, perfect. Okay, so little bit introduction about myself. So I have my bachelor degree and PhD degree in computer science, although I'm working at business school at the current. And I have experience in both industrial and academic environment. So I lived in 3 different countries. So basically, I finished my bachelor degree in China and I went over to Canada, finished my PhD degree in Canada. And afterwards, I actually worked in the healthcare industry for a number of years. And I realized that a lot of things we can get it done, especially apply artificial intelligence algorithms or machine learning algorithms at that time into the healthcare domain. So that's why I moved on to United States and to become a assistant professor at Purdue University at the Indianapolis site and teach computer science courses. And later, and last year, I've come to Oklahoma State University and become associate professor here as well. So that's my pathway of my over past a few years. So my research area primarily is in the natural language processing, large language models these days, and focusing on information extraction, especially the unsupervised key extraction, name entity recognition, causal relationship extraction from the text. And also I work with my collaborators on different QA project, question answering. So all these are different types of natural language processing project, and they evaluate using different metrics. I think some of you guys are coming from the computer science domain. And I also work with different professors based on the project needs. For example, construct a recommender system and utilize graph neural networks for recommender systems. And also we apply multimodal learning these days for the healthcare domain as well. So primarily, my research being funded by National Institute of Health and with the application to the healthcare domain. And I also work with some researchers in the network security domain just to apply these techniques to analyze the log files. So which I'll give you guys some idea how this works in the network security domain as well. Throughout my talk, if you have any questions, you can ask, and right, so we don't have to do a really formal seminar, so it's more like interactive. So if you have any questions, please let me know. And I'll first talk about the AI and LLM, or natural language processing application for the healthcare domain, and then move on to the fundamental NLP project, and then to the security project. So I'm not sure whether you guys have any background about biomedical research. Actually, NLP and AI these days has applied a lot to the medical domain. The reason is that we do have large amount of data, no matter it's electronic health record or clinical trial descriptions. So for all the clinical trials happened in the United States, we do have a clinical trial database and covers all the description of the medication and the clinical trial recruitment as well. And we also have user-generated, we call it consumer-generated text data as well. For example, the social media publish a lot of, or some of the medical forums and the consumer of certain medication publish their opinions about certain medications online as well. So on top of that, we do have medical literature. We do also have the medical guidelines. So for all the physicians, what they do is they use the medical guidelines to treat the patient most of the time. Although the recent days they promote evidence-based clinical treatment, but still physicians most likely is going to follow the clinical guidelines. And other than these different text data set, and there's a huge need how to create clinical support systems, which I'm going to introduce you some major systems we are developing right now to talk about why we need AI and NLP in these domains. Let's take a look at the complexity of the NLP in the biomedical domain, because biomedical domain is different from the traditional NLP domain. In the biomedical domain, there's a huge amount of research on word sense disambiguation, because physicians or patients, when they write information, is in the medical context, right? So discharge can mean different things in different medical contexts. It can be discharged from a hospital or discharge of certain fluids from a wound, or abbreviations are used a lot in the medical domain as well, especially when physicians write their clinical notes. They use a lot of abbreviations. So these abbreviations can mean different things based on the context of the biomedical content. So RA can mean rheumatoid arthritis or right arteries, right? So these could be different things. And also in the biomedical domain, name entity extraction, relation extraction are quite popular, because this information will help us to develop drug discovery and also to identify the phenotype, computational phenotype relations between the genes and disease, between symptoms and the cause of the symptoms, and the length, the duration of the symptoms as well. So all these we call it and name entity extraction or relation extraction. From the high level for biomedical data analytics or health informatics, so from the computational point of view, and normally we can describe our task into either predictive analytics task or descriptive analytics task. So when we think about the data source type, so we do have the electronic health medical record. We also have biomedical imaging data. We have a lot of sensor data as well. So in the future or in the current medical decision domain, normally we don't rely on one set of data. So we have to integrate multiple different data types, including sensor data, biomedical imaging data, and the structured data extracted from the medical record. And once we have this data set, normally we have to curate our data patient cohort. The reason is that sometimes we do not only use the diagnosis of the data set. So for rare disease, we have to curate certain patient cohort to make sure the patient have those certain disease or certain elements we are looking for. And then we construct our data presentation for the patient. So you can imagine we do have imaging data, we have sensor data, we have structured data, we have unstructured texture data as well. How we can construct data representation to present each patient is pretty challenging work. It definitely impacts the outcome, right? So also impact which algorithm or computation model we are going to use. So typical, we use vector space model, or we use graph model, or we use multi-model, different algorithms to integrate those data representations. So we either build the representation at the representation level, or we create the representation for different data types and integrate them at a prediction level. And the prediction tasks we normally do involve are outcome prediction, right? So what's the treatment outcome, whether the drug has any effect on the patient, or will the patient develop certain disease, or whether we are going to monitor the healthcare outcome. Those are different tasks. So based on the clinical needs. And there are some other descriptive analysis. Basically, we don't want to predict any outcomes. So we want to discover certain patterns, because often, for example, for cancer patients, when they go through the chemotherapy, and we don't want to predict whether the modality of the patient, probably we want to say, okay, how the patient feel about the chemotherapy based on the comorbidity status, right? So whether the patient develops certain disease, or how the patient develop different groups of not necessarily disease, the symptoms, right? So we basically want to group the patient based on the symptoms, and then look back whether the patient has certain comorbidities causing the different combination of the symptoms. So we call those as descriptive analysis. For descriptive analysis, we have different tasks as well. For example, healthcare disparity detection in the public health domain. So in that sense, we normally can utilize not only AI, sometimes we utilize statistical modeling as well to identify disparity detection, disparity in certain domain, for example, disease treatment and healthcare outcomes. But we don't try to predict outcome. We want to see whether there is any disparity in the treatment cohort. And we also visualize our data and do some topic modeling as well. So often my projects are task-driven. Okay, so what I mean by task-driven is we sometimes don't do a specific prediction task. We try to build a clinical decision support system to really, at the end, we hope it will going to help physicians in different areas, right? So one of the decision support system we are currently building is called personalized preventive care system. So what it does is, so as we know that for women who is certain age need to go through the mammogram to prevent breast cancer. And for patients who have family diabetes, they also need to go to certain preventive care to prevent diabetes. If they have any family history of diabetes, they probably need to go through the preventive care early enough. So how the physician determine the preventive care? So they have set of preventive care guidelines. And then we do have patient records. So we know when the patient has certain symptoms, or does the patient has any family history? Does the patient have any comorbidities? What's the lab test result for the patient in the history? So when physician make recommendation for patient based on the preventive guidelines, they're normally based on age and gender. They don't have enough time to look at complex and long patient history. So what we want to do is we generate a personalized preventive care recommendation system can help family physicians to recommend the personalized preventive care based on the family history, social history, and the medical history of the patient. So the first step we're going to do is extract information from guidelines and use large language model. So I'm going to talk about this project later. And on the other side, we're going to extract information from the medical record, and we use AI models to generate personalized recommendations so that this recommendation can be used by the physician and can be also used by the patient at the same time. And also this system will increase or improve the communication between the patient and physician about their preventive care, right? So help them to understand why they need to go through preventive care, etc. So another project we are working on is for the medical emergency services. It's also a clinical decision support system. So currently, I think probably many of you know when the emergency medical services, what happens is on the ambulance, when the emergency EMS providers try to save patient life, so they do need to follow again protocols or guidelines to give treatment to the patient, but at what time to give what type of treatment, they have tons of guidelines they need to remember. So and based on the complexity of the patient situation, it's how we can generate not preventive decision support for them to avoid medical errors and to provide support to guide them through the process, through what type of treatment they need to apply to the patient based on patient age, weight, and the comorbidities, symptoms, etc. So this is a project also funded by NIH. So what we does is we actually have all the first step is this is at the very prototype stage. So we have the providers wear smart glasses. I don't know whether you guys know the smart glass. So basically they wear the smart glass. The smart glass will capture all the images and capture all the communications between the patient and the providers during the treatment process. So then once the conversation's been captured, so we're going to use the artificial intelligence based algorithm to transcribe all the communications, and then we use different large language models and integrate them to populate the electronic health record automatically. So in the traditional way is they need to go back home and go back to their office, typing all the patient status. There's no decision support while they are saving patient life in the ambulance. So what we try to do is we are going to use the smart glass and enable the automate documentation of the EHR record. On the other side, we're going to try convert all the medical guidelines used for emergency medical services, and we use generative AI through an active learning process to convert those guidelines into digitalized workflow. And then by using the workflow and the medical record, we're going to generate recommendations for the paramedics, so the providers who is on the ambulance. And then we can generate an alert, we can generate recommendations. The alert basically served as a decision support tool to help them to avoid any possible errors. For example, medication errors, if the patient is a young patient, the dosage of the medication should be at what level. So basically we customize those to recommend, generate an alert to give them guidance on how much medication they should give to a young patient, especially pediatric patient. So these are both projects funded by National Institute of Health. And now I want to go through a little bit details about a few projects we've done and from the computational point of view. All right, so first project I want to talk about is how we use deep language model to extract symptoms from clinical notes, and then how we apply to that framework to analyze COVID-19 data and from the social media to understand whether we can actually use the framework to extract the COVID-19 symptoms mentioned in the social media. So this is early work. We've done this during the pandemic. At that time, we don't have really the large language model. Those GPT models is not developed at that time. So what we've done is we develop our own deep learning based language model to identify the symptoms from the clinical notes. So identify symptoms from clinical notes is not an easy task. There are some existing tools that can extract symptoms. For example, UMS MetaMap can extract symptoms from certain texts, but sometimes those are not true symptoms. For example, take Tylenol if fever. So fever at this time is not a true symptom, right? So really we are looking into develop a framework to identify the true symptoms, but exclude the not true symptoms. Okay, the true symptom would be those actual direct symptom mentioning and also complaint statement. The not true symptoms include a lot of different variations. For example, negation. The patient does not have the symptom. They mention not feeling tired. Conditional symptoms like take Tylenol if medication symptom, take Tylenol if fever, or condition symptoms, if you have chest pain, go to hospital. Resolve the symptoms. The symptom has been resolved overnight already, so the patient does not experience such a symptom. And there are other symptoms, not true symptoms as well. So we try to cover different not true symptoms by using our framework. So now the data set. So basically for this type of works, we need human to annotate the data set to create ground truth for us. So we basically work with faculty in the School of Nursing. So they go through different clinical notes and annotate which one is the true symptoms. So they don't annotate the not true symptoms at all. But we definitely have them to look into, okay, these are the not true symptoms, these are the true symptoms. We go through total more than 16,000 of sentences within the original clinical notes in the medical record. And here is our framework. So this language framework including two components. One is called deep symptom, the other is symptom. So basically we look at the correlation of the words based on the syntactic relation and also semantic relations between those words. So for semantic relations, we use the typical name entity recognition approach. So we use the BIEO annotation strategy to annotate the actual symptoms and feed that into the BERT model and feed that into the conditional random fields. And this is typical name entity recognition by using a BERT model. On the other side, we utilize the basically the syntactic dependency between the words and feed those into the deep learning network. So we didn't use the BERT model at this time. So we feed all those dependencies into the deep neural network, and then we predict the outcome. So this one is based on syntactic, one is based on semantic. So how we integrate these two parts, we basically look at the length of the prediction result. If the prediction result has more than 3 words, so we combine both. Otherwise, we just rely on the one side on the semantic part. All right, so for any computational method, we have to compare with the baselines. And in this research, we actually compare our model against at that time, most of the popular models like Clinical Bird, Bluebird, BioBird, etc. And we also look at disable, because we have 2 components. How about we only use one of these? Which one actually works better than the other? Or we have to combine both, right? So. And for the evaluation metrics, we look at exact match and relaxed match. So exact match, we have to match all the words within each of the symptom, and in order to calculate precision recall and F1. For the relaxed match is more word-based. We don't have to get all the words, so we can use the phrase-based and calculate word-based recall, precision, and F1. And here are some examples of what scenarios our model works better. Okay, so basically, some of the terms for the phobia actually are not included in the UML's meta map, which is a big ontology used to identify the clinical terminology in a given text. So they do have different semantic types, and one of them is symptom. So we compare to that ontology based approach. And then we also compare ours with other ones to identify. So basically, our model has advantage at identified those long and complex symptoms, for example, more than 5 words. And also the ones are not included in the original ontology, for example, weight loss for those. Of course, we want to see, right? So for any computational method, we want to see how generalizable our method could be to other data sets. So we look at the social media data set. Social media data set is different from how physicians write their clinical notes because those are written by consumers about their symptoms. So we look at COVID-19 related data, treats published between 8 weeks from the middle of March till the early of May. And we also have annotators from School of Nursing and annotate all these symptoms they think actually experienced by the user who submit these treats. And we didn't really annotate a lot of treats in that situation. To test our performance, we annotate 200 treats just to see whether, our performance is comparable when we apply to the clinical notes. And as you can see, the Cohen-Kappa value between the annotators, so this value indicate consistency between the two annotators is not as high. The reason is that the understanding of whether the symptom experienced by the user is different. For example, look at this sentence, okay? There's a lot of anxiety and uncertainty going around with the pandemic, so they want to make informed as easy and stress-free as possible COVID-19. So anxiety actually is not a symptom experienced by the user who submitted treats. It's just the description about anxiety in our community. So in that example, right, so two different annotators could one annotate as a symptom, one annotate as not symptom. That causes the inconsistency when we annotate the social media data. And as well, we notice that our performance, even we apply the relaxed match matrix, our performance on the social media data is not as high as when we apply our framework to the clinical notes because our framework has been trained on the clinical notes and has not been trained or fine-tuned using the social media data. So then we look at how good our system identify, the CDC mentioned symptoms about COVID-19, and definitely we can identify those CDC symptoms, and we also identified a bunch of new symptoms are not being mentioned by CDC and going around since the beginning of the pandemic till early May. So what we've learned is really we definitely for any these type of clinical NLP task, we sometimes need to adjust our algorithm based on the context, right? So for social media context versus medical record context, maybe we need to fine tune our models to improve performance. But on the other side, we also learned that for to extract those information, definitely we need to develop certain algorithms, and algorithm maybe need to change to identify, social economic factors, family history, medication, gene mutations, because the annotation would be different. But on the other side, the annotation is labor costly and it's not easy. And we look at other methods to augment the annotation process. We call it active learning. So we are implement that active learning process by integrating with generative AI. So we have built a human AI interaction cooperation network to improve the annotation efficiency. Otherwise, it's just labor costly. The other work we looked at is the causal relation and the extraction from the medical literature. So, the causal relation actually is quite, well known, right? So what event caused another event? So, but in biomedical domain, it's not as straightforward because the cause and the result, so the relation is not simply noun or noun phrases. Rather, there are more complex phrases. For example, SIM21 caused a reduction of 12% of cell variability, right? So reduction of certain things happened. So there's an action item. It's not really a simple phrase. If we just get a reduction, it's not include the full context. So that's why we look at how we can effectively extract causal relation from medical literature and using a dependency tree-based patterns. Here, I just go through the architecture of the system. Okay, so in this research, basically we create bi-directional LSM plus attention level to extract the causal relation out. So the attention layer basically is responsible to identify which part actually trigger the output prediction, and we use the softmax on top of the second layer LSTM to extract the causal relation out. The input to this system, to the BioSTM, are the edges embeddings between when we convert the sentence using the syntactic analysis. So we do have the name, the type of each words, and we also have the edge to show the dependency between each word or phrase. So we use this edge to embed the input. So then we can identify which edge actually trigger the causal relation. Okay, so that's the whole idea in this research. So when we implement this model, obviously we had the annotation, and we annotate about 300 sentences in the biomedical literature. And then we compare our model against the baselines, and the performance is significant than the baselines, but it's not really high. Okay, so later we actually look at how to use large language model to improve the performance. We haven't finished the experiment yet, so I'm not going to talk about that today. But the good thing with our model is actually it works better on the non-complex phrases. So that's we want to demonstrate. So here are some examples. For medical domain, it's not a simple two phrases. It's the complex cause and result relation. And then since we have the large language model, right? So GPT model, Llama model come to play in our world. So, and last year we started looking into the basics, okay, how to apply large language models to analyze our medical data. Especially, we want to look into social determinants of health and medical family history extraction from the clinical notes. So we actually look into 3 different large language models by apply zero-shot learning at the beginning, because we want to see, okay, without giving much interruption or input additional instruction to the large language model, how good this large language model are extracting those social determinants of health or family history. And again, we have to do the annotation, and we have 2 different collaborators from the hospital and annotate these clinic notes for us. And then we basically develop the framework so to extract the clinical notes by using these large language models. So in these scenarios, because for social determinants of health, we want to cover different categories. Okay, so in this work, we try to extract demographics data from the clinical notes. We try to extract different types of social history, including employment status, alcohol use, tobacco use, drug use, education status, living status. For the family history, we want to extract observation. So what type of disease the family history has, or vital status, whether any side of family passed away or not. So because these information are quite important for physicians to make decisions in doing their treatment to the patient. So these are the few examples. Okay, so give a sentence. So these are the examples we annotated. So those are the ground truths. So for example, the alcohol use, they basically either deny the alcohol drug use or actually, and what happened, or how many years they are on alcoholism, or do they have any alcoholism or things like that. So for the interaction with the large language model, as I mentioned, we want to minimize the instruction. We really didn't train any of these, fine-tune any of these GPT models or any of these large language models. We just give a description and output. We instruct the large language model to output certain structures so that it's easy for us to dump the result out. And because we look at different categories of the social determinants of health, so basically we apply the post-procession to put those, extract the social history into different categories, and based on the keyword-based search approach, and also based on the embedding-based similarity calculation. When we evaluate the performance, we use the name entity recognition evaluation metrics that typically used for information extraction, no matter what type of information extraction we're doing. So, and obviously it's based on precision recall and F1. So what we noticed that's interesting thing happened with the large language model is we know that large language model sometimes generate hallucination, right? So actually not only hallucination, so they can also change our original content. Even we specifically mentioned that do not use new words, use all the input in the original input text. So for example, original text could be never smoker and the output will be never smoked, which is different, right? So that causes the evaluation metrics. If we use these precision recall, we are going to match individual word and in order to calculate the precision recall and F1. So then we think no, never smoker and never smoked, semantically they mean the same thing. So that's why we apply another different metrics, which is cosine similarity metrics, to measure the similarity, to measure the performance. So we set up the threshold as 0.9 in order to say, okay, if the similarity between cosine similarity using the embedding based approach is above 0.9, and they are counted as a match as well. So these are the different results. So as we can see, and for the demographics, the performance is pretty good, age, gender, ethnicity. But for the social history, family history, the performance is not as good as demographics, right? So, but if we switch to semantic evaluation metrics, the performance slightly better than the NER-based metrics. So let's take a look why some of them does not work well, right? So because as a computer scientist or as a data scientist, you not only present the performance, you also need to understand why, whether there is a chance we can improve, right? How we can improve it. So we look at those situations, we found like one reason I mentioned before is generate different words, and although it's keep the same semantic meaning, but we use the threshold 0.8, 0.9. Sometimes the threshold is a little bit high than the actual the similarity. So when human read those two terms, maybe the similarity is good enough, but when we evaluate it, it does not reach our threshold. So that's why it does not capture as correct extraction. And also the GPT model not good at, finding the ground truth from the large amount of input, especially if the result is cross different sections. So it will not identify those and summarize them, extract them out. So that's another thing we find. And also, even we set the temperature into 0, so output was still inconsistent. So that's another problem we are facing. So we're solving this problem by using different strategies at this time, because we don't want the GPT model or large language model to produce different output when we use it at different time. So that's definitely we're working on. And another project I want to quickly mention is because we are extracting information from the healthcare, like documents, right? Electronic health record. On the other side, how about the guidelines? Because I think analyze medical record, a lot of people is doing that. How about the guidelines? Guidelines used by physician almost all the time, and we need to process guidelines no matter it's for primary care, for emergency physicians, or because they use the guideline all the time. So how can we process guideline so we can integrate this guideline with the medical record to generate decision support system? So this research is we are going to look into how we can apply zero-shot learning to extract assessment criteria or medical services from the preventive guidelines. So these preventive guidelines are published by U.S. Preventive Service Task Force, and it's been updated once a while just to capture the evidence-based medication or treatment, because based on population change or based on new evidence, they need to change the guideline to make sure patient goes through those preventive care in a certain time. So for your knowledge, so we do have rated guidelines published by the task force, and A means strong recommended, B is recommended. Both categories are covered by insurance, no matter what type of insurance you have. So a patient does not need to pay anything to attend those preventive care. And so in this, because our objective is to integrate these guidelines with the medical records in the system so that we can analyze medical record against guideline to generate recommendations for the patient for them to go through the preventive care. So we basically develop this structure to match the EHR data structure so that we can analyze each element against the medical records. So we try to extract the information from the guideline, including age, gender, ethnicity, comorbidities, or disease they mentioned as the risk factors for certain disease, for example, breast cancer. We also extract social determinants, family history, because all those impact the development of certain disease as well. And what type of preventive care services they need to get it done, whether it's mammogram, medical imaging, or counseling for mental illness, or lab test for diabetes, etc. So there are different type of preventive care services patients need to go through for disease prevention. And in this research, because we are the first one to analyze preventive guidelines or any medical guidelines. So that's why we first tried to use the zero-shot learning. We applied, at that time, we haven't used the latest version of Llama. We used PAMA 2, invented by Google. And so we basically go through the post-processing in order to match against the ground truth and also our extraction. So these are the annotation. Okay, so we have the annotation tool so that the user can annotate the guideline, because guideline is a large PDF document. So we have to have the physician annotate all the factors I just showed you in the previous structure. And then by using the annotation tool, the backend will generate a JSON document, and then use the JSON document. We're going to, as the ground truth, we're going to extract the data into the JSON document and for the evaluation as well. So when we use large language model to extract information, we use the post-processing to either lowercase all the extracted results and generate abbreviations and things like that. So for the guidelines, okay, so how many guidelines we have? Actually, we evaluate the total 28 guidelines, but among these guidelines, okay, these guidelines apply to different populations. Some of them only apply to male, some of them apply only to female. And also they have age constraint as well. Some of the guidelines only apply to age older than 65 years old. Ethnicity risk factors, some of them mentioned ethnicity risk factors. Some of them also mentioned about disease history. So some of disease history is required when they attend those preventive care. Some of them are more like risk factors. And many of them mentioned about social determinant of health, whether they have smoking history or alcoholism history or things like that. And these are different exam procedures. So when we look at those examples, okay, so those are pretty straightforward examples, and this table shows you the ground truths of the different categories of information in terms of number of words in the ground truths, because those are guidelines, right? So they could use different words, and we don't want to change how they frame those age and the gender and medical history in the original guideline. So these are all annotated from the original guideline. And now we look at the performance, and when we look at performance, performance is really on average is not high. If we look at the NER evaluation metrics, precision recall and F1, because we do need the word to match, right? So even they mentioned like Black Americans, original ground truth is African American, it won't only get half of the match, right? So it does not match at all. So that's why the performance is not high. So this is some examples we look at. For example, the why it's like the performance is not high. Many of the reason is caused by different words, but with similar semantic meaning. Like we use that in the social determinants of health extraction. And also they use different concepts. Sometimes it's broader concept, sometimes narrow. For example, for the extraction, the ground truth is a psychiatric disorder, but the output for GPT-4 is depression. Depression is a narrow concept for the psychiatric disorder, right? So those actually causing the low performance of the extraction by using the zero-shot learning extraction. So, and we also look at the guideline based. Let's say, okay, if we want to use zero-shot learning, can we actually integrate any of these guidelines without much errors and with the electronic health record? So we do find like some of these guidelines has pretty good performance for breast cancer, and breast cancer only involves 3 categories of data extraction, including the gender, age, and the history. Okay, so all of those are pretty good. We can identify all of those pretty good. But some of these, especially for the unhealthy drug use screening, some of these we cannot get a good performance, alcoholism, and it's pretty low performance as well. One of the reasons is when they mentioned about alcoholism or drug use, and because of the social determinants of health was not really fully correctly extracted based on original content, but some of them semantically meaning is there, but just not exact match. So in conclusion, so in order to eliminate hallucination, or let's say we don't want the large language model to extract information semantically the same, but using different words, so we try to use ROC to reduce the what is really, it's not really hallucination, but still generation of new content. So, but in some case, we want, I'll explain in what situation we probably do not want to limit the generation of new content. And we also learned that really these generative AI models can help integrating those guidelines with the medical record, but still a lot of post-processing or fine-tuning of those models using the guideline, the terminology used the guideline, before really we can integrate those into the clinical system to generate disease support. But that's our first step, right? So now let's move on to the large language model for unsupervised key phrase extraction. So this set talking about more fundamental computer science research instead of apply to the clinical research. And first work we've done is, so let's talk about why we need unsupervised key phrase extraction. Key phrase extraction is used a lot in the information retrieval domain. So think about Google. So when we input the search query in the Google, so we want to find the most relevant documents returned, right? So how do we know those documents are relevant or not relevant? Each document, we first identify the key phrases, right? So we don't want to identify all the words and index all of them the same way as we index the other papers. So we want to say, okay, this paper has these key phrases, that paper based on the main topic of this paper, right? So, but for key phrase extraction, it's not an easy task. Often it's utilized. Sometimes we utilize supervised key phrase extraction, but if we want to use supervised approach, basically we need to have labeled data. So in a lot of situations, other than literature published in the scientific domain, we do define key phrases for some of the papers, but for information published online, there's no key phrase defined. So it's also not a lot of human label involved. If we want to utilize supervised learning, we have to label the key phrase as well. So that's why it's motivated us to look at unsupervised key phrase extraction. On the other side, I was thinking about how we can apply this approach to clinical domain as well. So that's why we start developing fundamental algorithm for unsupervised key phrase extraction. The first work published in the EMLP is we used at that time BERT embeddings or this transformer model. It gets really popular and it's good at a lot of NLP tasks. And then we were looking at how we can utilize the BERT model, especially the transformer model, to identify key phrases by given any input text. So what we did is we actually generate a few candidates. So in the traditional key phrase extraction words, all the candidates are noun phrases. So we get all the noun phrases by using the syntactic analysis and from our input text. And then we measure the cause attention. We first measure the self-attention. So for BERT, you do know that for each word, it receives attention from different words within the same sentence. So we first retrieve the accumulated self-attention. So any words receive attention from other words within the same sentence. If the higher attention is received, so it has higher chance to become a key phrase. We also look at cross attention between the candidates, and again, it's the sentences because the self-attention managed within the same sentence, but how to measure the candidate against other sentences which do not have this candidate, right? So we use a cross attention mechanism to extract the attention out. And then we also measure the document attention by aggregate all the sentence level self-attention to the document self-attention. And finally, we use candidate self-attention to measure against document self-attention and calculate cosine similarity and for the integration. So for this work, we definitely compare all the baselines. And at that time, we do have a few baselines. Some of them are statistical method-based key phrase extraction, for example, YAC. YAC, how they identify key phrases, they use the statistics of different candidates. For example, whether the candidate is uppercase, occur in the first paragraph, occur in the last paragraph, that type of thing. There's no learning mechanism. And there are other ones that utilize learning mechanism and to rank the candidates. So we compare our approach against the baselines by using the extract the top 5 key phrase, top 10, top 15 key phrases. And the key phrase extraction will also use precision recall and F1 for evaluation metrics. And our performance is better than the baselines in most of the situation, other than at the top 5 and the SF rank and the top 10 is better than us for this inspected data set. Semi-eval 17 and semi-eval 10. So our performance is consistently higher than the SF rank and other ones. So these triangles means we did the statistical testing to prove that the improvement is significant. And also this slide shows us the statistics of these different data sets. So for semi-eval 10, so it has less document because it's unsupervised. We don't need to split in training and testing. And for semi-eval 10, it's a long document set, has much more sentences than semi-eval 17 and inspect. obviously for computer science paper, we have to do the ablation study or, do a comprehensive comparison. So we did draw the precision recall curve on three different data sets to show that our PR curve is better by using the top 60 ranked candidates and for each compared to the baseline method. Other than the inspect, our performance is slightly lower than the SF rank. That's consistent with our table result presentation, but on a semi-eval data set, our performance is way higher than the baselines. So for the ablation study, we look at, because we do look at the integration between the document and the attention versus self-attention. So we actually limit one of the attention mechanism to see whether how much it impacts the performance, and we change the integration ratio as well. So this set we definitely show the ablation study of different parameters used in our work. And here we shows our extraction again is our attention rank again is the most competitive one as SF rank. So we see that it definitely highlight quite similar keywords, but the color is actually shows you the rank of the importance of the keywords, right? So, and most of the time they both can identify the key phrases the same, but the rank would be different because rank matters, right? So rank when we choose top 5, top 10, top 15. So how good each algorithm is at ranking of this importance of keywords. That's indicate the good of our algorithm. And then we move on to the graph model, because we use cross attention and self attention by extract attentions built into the transformer after transformer is pre-trained, right? So how about we don't use the attention to cross attention, self attention, and how about we use a graph model to mimic the relation between the document, candidate, and sentence. So another work we've done is we argument the model. Okay, we change the model, we mimic the attentions, but we don't use the cross attention. We change the relation into the graph, and then we apply the graph model on top of these to identify the key phrases. So we compare our approach with all the baselines, and at this time we add another data set. Why we're adding this new data set is this new data set is also a long document with more sentences here. And then we actually demonstrate our model performs better than the attention rank, which we developed previously in most of situation, but in the semi-eval 10, and we didn't beat the attention rank. But in most situation, the age rank, actually, the graph-based model works better. And we also did some ablation study, but whether we should stemming our candidates or not stemming our candidates, and do we need to include document notes or sentence note, etc. So we did the ablation study. And the last recent work, we look at a large language model. Okay, this work is going to be submitted to PAKDD. And then because we have the large language model, so how about we don't use BERT, we use large language model to generate key phrases, and then let's see how it works, right? So whether maybe large language model already good enough. But when we did the result, we found like if we use short learning, large language model does not work well, then even our attention rank in some situations. So that's why we augment a large language model using a graph-based model and to rank the candidates. So that's we actually compared more than 17 different baselines, because there are more baselines we need to compare. All right, so I guess I'm running out of time here. So I'll probably quickly go through the security, okay, intrusion detection. So the basic idea here is we apply the large language model to analyze log files. And this work published this year as attracted a lot of attentions from the domain. So for the
Sorry,
intrusion.
Dr. Lu. Sorry, Dr. Lee. Dr. Jahan, do we have the meeting time extended because it's already 11:28? I'm afraid like if it is going to automatically out. Dr. Jahan? Dr. Jahan, are you there? I think she's not there.
Fine. If it's already out, it's already out. Doesn't matter. Yeah.
Okay, so
Yeah, I just quickly go through this. Just we analyze the log files and to see whether we can use large language model to analyze log files for the intrusion detection. For this research, is a supervised learning, and we try to fine tune the model or we use the baseline, which is a zero-shot learning. So actually, fine tune the model works better than the baseline because we fine tune the large language model using the log file. It has the a basic knowledge about the intrusion detection, and we visualize our data. We actually using the transhape to interpret the result because it can highlight what section of the log trigger, whether it's normally or it is normal traffic. Okay, so because interpretation is quite important these days, not only telling whether it's intrusion or it's not intrusion. And so that's my funding the current funding, that's all my collaborators within the United States and outside of the United States, and that's all my lab members, and that's all my funding agencies, and thanks. And maybe one quick question.
Yeah, basically, audience, sorry, we are running out of time. So first, let me show you how to post the questions online. Then, because I don't know when this will time out, so let me quickly show how to post the questions. If in case this meeting times out, then let me show you how to use this. So I have provided our website link here. So go to Building Scalable Predictive Model 2024. So here is your Q&A forum. And then here you can submit the questions, pressing the submit form. And you can put your speaker to whom you wanted to submit your questions, and you can have your questions submitted here and click a submit button so that it gets submitted to the speaker. And it's open. It can be accessed by the speaker as well as the people like students and audiences. So even the speaker can open it and answer to the question and submit so that the anyone can view it. So I'm just telling this because if in case I think the time is extended, but still if in case if we run out of time or the meeting exits, please, I would strongly recommend you guys to submit your questions here to Dr. Luo as we ran out of time. So I hope this is clear here. So I'll give you 5 more minutes to quickly have any questions that you wanted to ask Dr. Luo now. Otherwise, I would recommend everyone to submit questions here in the WIDS website in our page. Anyone has any questions to ask Dr. Luo? I think no one is opening up now. So let me ask one quick
That's fine.
question.
Yeah.
Let me ask one quick question before the session ends. So I just wanted to understand few things quickly. So you talked about dependence. I mean, two, three projects were there, right? So you talked about the last one. Let me ask about the last one, the key phrase extraction and building the graph on top of it. So
Yes.
cross attention and then the self attention. So a question related to that. So what I understood from what you told is that the LLMs, when they generate the answers, the context might be different sometimes. So the meaning will completely change. So this is a general question. I'm trying to relate two, three things to it. And there is something that you talked about the guidelines for the previous projects.
Yes.
So there you mentioned that we either use LLMs or without using LLMs, you're trying to integrate the guidelines with your existing decision support system, and then you try to predict to show that LLMs are not performing better. Or I understand by using LLMs, you can advance it, improve it, but it also has its own disadvantage of giving wrong results, wrong meaning, wrong context, right?
Correct.
So
Yes.
what were you trying to prove there? Are you trying to promote LLM or are you trying to
Yes.
say that
We
LLM is
we
not
have
good?
LMS is much more efficient, and but you have to first. So a few things we need to get it done is first to customize LMM towards a specific task or towards medical domain. So we do have ME Llama these days but still it does not really process the guidelines well because the guideline has not been used to fine tune those large language model at all. So fine-tuning large language model towards a specific domain, in medical domain is different, and in the computer science we have different application to different other domains, right? So you have to fine-tune the large language model into a domain-specific task. Okay, so that's first of all. Second is when we have a large language model generate result, we want to control what type of information the large language model is using. So we don't want to say, okay, go wild and generate any information based on the knowledge space, right? So we are trying to use either RAG or additional constraints to supplement large language model when they do information analysis.
Okay, you mean to say that you're using additional support along with this customized LLMs
Yeah,
to
yes,
basically
yes, yes.
improvise. Don't directly blindly go with LLMs as it generates answer
Correct,
doesn't mean
correct.
that you're going to get a right output. So that is your
Correct,
main point.
correct. So based on our user evaluation, large language model, even we integrate 5 different large language model, it still generate information that is not necessary in the original input. So it can already, sometimes semantically they are the same, but sometimes, the physicians does not want to see that change. So they still want to see what's mentioned in the original input. So that's pretty important.
I also heard that you're saying the human annotation being expensive. So using
Yes,
LLM
yes,
to
yes.
attach labels is better, So this means the overall idea is to say that the cost cutting can be helpful in this case by using LLM with other supports so
Yes,
that you
yes,
don't have
yes.
to go for human annotations, go for AI annotation. So that was another
Yes,
point. So
yes,
another important question about dependency parse tree that you talked about. So in that project, you meant you had that subject verb. I also worked on dependence parse tree before. So I have a related question. So you said that you are finding the causal analysis, like which
Yeah,
caused this. So that
yes,
is
yes.
based on the path of like whether it's based on the subject or noun or verb or
Yeah,
things like
yeah,
that.
yeah. It's depend on dependency tree. Dependency tree is based on the syntactic analysis. So you know the
Synthetic.
Stanford NLP package. So
Yes.
they extract the syntactic dependency between the words automatically. So we use that generated edge, and feed that into the BioSTM with attention layer. And with that attention layer, we actually can identify which edge link to the causal relation. Yeah.
So that edges can vary based on the samples, right? Or are you trying to say that overall for this particular data set, the major
The edge,
relationship?
so if you look at the edge and the attribute of the words, they are limited because the edge will be the type, right? So we don't
Yes.
input the actual words. It's
Okay.
basically the input actual words. It has the embedding of the word semantic meaning, but we also input the noun, whether it's a noun,
Noun and
adverb. So all those are standard, right? So it does not
yes.
change with the change of the meaning of the
So my question is here. I understand that the noun relationship between verb, that is what you're going to see that. So
yeah.
here is I'm confused. Like you have a overall like you are having a data set. Like I don't know how many data set you processed with that.
Uh-huh.
So for example, let's assume there are like 100,000 data samples are there, and where you
Mhm.
identify the relationship and just go with the noun verb kind of relationship. And
Yeah.
oh, at the end of the day, are you trying to say that, okay, most of the relationships that identify the causals is based on subject to noun, noun to verb, or something of that sort? To
No. This is supervised learning, and the relationship still build upon like you said, it's all the supervised learning are data driven, right? So it's
yes.
not different from the unsupervised. So it's if the data, so the data covers all the diversity. We try to cover all the diversity between the nouns, adverb, adjective, and all the edges between those words, and also the embeddings between of the words as well. So the embeddings capture the semantic meaning, and the edges and the attribute of the words capture the syntactic meaning, right? Relation between the words. So we try to use those to combine to get the importance of the edge out in order to inform whether they have any causal relation or no. Yeah.
Oh, okay. I get it. I get it. Yeah.
Right. So you cannot purely based on the syntactic or purely based on semantic. So normally for NLP, you traditional like human read a language, read a sentence. We basically based on the syntactic relationship and semantic the words, right?
Yeah.
So that's a mimic. Even you look at transformer, how they train the transformer, they actually mask certain words within the
Yes.
sentence, right? So those words has meaning. Those words also has syntactic dependency between
On the previous
words,
and
right? So of
afterwards.
other words as well. So
Yes.
it's idea, it's the same, but just we apply it in a different way.
Oh, okay, okay. Now I understand. I
Right.
get it. I mean, it's a very exciting. All the projects that you discussed, I particularly enjoyed a lot. I have a few more questions, but I'll post it on the form because
Yeah,
we've
yeah.
been running out of
Feel free.
time.
Yeah. Yeah.
So hope
My research is
everyone.
primarily in the NLP, in the
Yeah,
natural language
I
processing.
really enjoyed because each and every topic when you discuss most of it, I also worked. At least if the paper is not published, at least I worked in a project to try out some experiments.
Yeah.
Certain worked, certain didn't work as experiment, but at least I have an idea of what you spoke, and it was really interesting and very interactive, and a lot of knowledge also I had, like overall knowledge I was able to gain. It was
Yeah.
very, very,
Okay.
very wonderful session. I really enjoyed. And I hope that audiences also should have gotten some idea from this, especially computer science background. So there are some new PhD students here, so they also might have got some idea on how this works with Gen AI, LLM, and NLP world. So great presentation, Dr. Luo. I appreciate your time and effort, and I think we are running out of time. Thank you so much. Audiences, please utilize this and post all your questions so that Dr. Luo will have enough time to answer, because after this exam week, they'll have some time to answer back. The question forum is open, but I appreciate you to strongly post as soon as possible so that they can answer after the exam week. Thank you so much, Dr.
Great.
Luo, and all the audiences for participating in this. Thank you. Thanks all.
Thank you. Thank you.
See you
Bye-bye.
then. See you in the next meeting. Bye. Guys, you can exit. I'm just trying to download the recording. It will get saved.